Hello, IB Bio students. Today we're going to continue with topic 8.3, and we are going to look at the light-independent reactions. Before we do so, let's quickly just summarize the events of photosynthesis as a whole so we can truly understand what will happen in the light-independent reactions. So today we're going to focus on this right here. But keep in mind that the light-dependent reactions, they've already done their job, right? They took that light energy from the sun and they converted it into chemical energy. We know that the chemical energy is being carried in these two molecules, NADPH and ATP. So now these two molecules carrying the chemical energy are going to go into the stroma of the chloroplast, and they're going to be involved in the light-independent reactions. Now, when they provide the energy in the light-independent reactions, they're providing the energy for carbon fixation. So that means that that carbon dioxide that's coming in from the environment is going to be fixated into organic compounds that the plant is going to be able to use. And we know that the most common organic compound is glucose. So that's the overview of what we will be looking at today. So now let's go and see the details. All right, so here's the basic understanding. In the light-independent reactions, a carboxylase catalyzes the carboxylation of ribulose biphosphate. So this carboxylase is an enzyme, and this enzyme has a name, and we're going to call this enzyme Rubisco. It's got a bigger name than this, but we can call it Rubisco, and you learned this back in topic 2.9. So now we see how the light-independent reactions are going to use the chemical energy that's derived from the light-dependent reactions, and we're going to see how the light-independent reactions are happening in the stroma of the chloroplast. So collectively, the light-independent reactions are known as the Calvin cycle, because the carboxylation of ribulose biphosphate, the reduction of glycerate 3-phosphate, and the regeneration of ribulose biphosphate is part of the Calvin cycle. So we're going to see that the Calvin cycle can be summarized into three main steps, and that's what we're going to focus on right now. All right, so step one is carbon fixation, and let's take a look and see how that happens. So step one, the Calvin cycle, right, which is part of the light-independent reaction, is where it all begins. And it begins with a 5-carbon compound called ribulose biphosphate, or we can simplify it as RUBP. So here we have the ribulose biphosphate, and when this ribulose biphosphate catalyzes with an enzyme called Rubisco, with carbon dioxide, then what is it going to make? It's going to make a very unstable 6-carbon compound. So here we see that happening. Ribulose biphosphate gets catalyzed via an enzyme called Rubisco with carbon dioxide to make a very unstable 6-carbon compound. That's what we refer to as carbon fixation. Now, this 6-carbon compound, because it's unstable, it's going to break down into a 3-carbon compound called glycerate 3-phosphate. Glycerate 3-phosphate. So, how many 6-carbon compounds are we going to make in this process? Well, since we start off with 3 carbon dioxides and 3 ribulose biphosphates, then we're also going to make 3 6-carbon compounds. Okay? Now, when this breaks, each 6-carbon compound breaks into 2 3-carbon compounds that we call GP, or glycerate 3-phosphate. So we're going to end up with 2 3-carbon compounds per 6-carbon compound. So if we do the math, 3 times 2 gives us 6 GPs, or 6 glycerate 3-phosphates, right? Because we start off with 3 6-carbon compounds. Each carbon compound gives us 3 carbons. So 3 times 2 is 6 GPs. So what happens with this GP, right? Well, that's step 2 in the Calvin cycle. So let's move right along. So glycerate 3-phosphate, or GP, is reduced to triose phosphate using reduced NADP and ATP. So here we have the 6 molecules of GP, or glycerate 3-phosphate, and this molecule is converted to triose phosphate. So let's keep in mind that GP, and I'm going to move this up here a little bit so you can see, GP is a 3-carbon compound, and triose phosphate is also a 3-carbon compound. So if we start off with 6 GPs, then we're going to end up with 6 TPs, which is the triose phosphate. Now, this reduction, though, is just a conversion. So we're just converting this molecule to this molecule. Now, that requires energy, and it requires a lot of ATP. So each GP requires 1 NADPH and 1 ATP to form the triose phosphate. So a single cycle, one turn, a single cycle is going to require 6 molecules of ATP and 6 molecules of NADPH, because we have 6 GPs in one cycle. Okay, so this costs energy, and we're using the chemical energy from the light-dependent reactions. So now we have our 3-carbon compound, and what's going to happen? That's the third step. So in the third step, we have the regeneration of our UBP. So the understanding is that triose phosphate is used to regenerate our UBP and produce carbohydrates, and ribulose biphosphate is reformed using ATP. Because again, this is a cycle, right? So let's look and see how the regeneration of our UBP happens. Before we do that, let's keep in mind that our UBP is a 5-carbon compound, right? And let's also remember that TP, or triose phosphate, is a 3-carbon compound. So we have 6 of these 3-carbon compounds, triose phosphates. Now, of the 6 molecules that we're starting off with, one molecule of TP is used to form half a sugar molecule. So then that means that the Calvin cycle is going to have to go around twice to get one full single glucose molecule. So two cycles to get one glucose molecule, okay? Because just one cycle gives us half a sugar, so we need 2 cycles for one glucose molecule. So then that means that if we go back to just the one cycle, that means that I have 5 molecules of TP left, right? Now, triose phosphate is a 3-carbon compound. So the remaining 5 TP molecules are recombined to regenerate stocks of our UBP. So I have 5 molecules of triose phosphate, which is a 3-carbon sugar, that will be equivalent to 3 molecules of our UBP, which is a 5-carbon compound. So our UBP is much bigger, so the 5 molecules of triose phosphate will only be enough and will only provide enough carbons for 3 molecules of our UBP. And we require energy for the regeneration of our UBP. So that is going to require 3 molecules of ATP for this whole regeneration to happen. Okay? So that is the light independent reaction. Make sure you review it. Make sure you understand that it's all part of the Calvin cycle, and that the Calvin cycle can be simplified into three main steps that we just saw: carbon fixation being the first one, reduction of GP being the second one, and regeneration of RUBP being step 3.